Okay, so let us continue our proof of the fundamental theorem of finite abelian groups. We have seen only a part of the proof, the beginning part, where we did something. Namely, we did this. G, of course, is our finite abelian group, and recall that we are under the assumption that the order of G is of this form for some positive integer n and some prime p. We started the proof by considering an element A1 in G having maximal possible order. Now that order, of course, will itself be a power of p, and we assumed it to be p to the power n1. And we denoted by capital A1 the cyclic subgroup generated by this element, small a1. Okay, and then of course we did some other things and came across an element A2 again in G whose order is p to the power n2, and we denoted by capital A2 the cyclic subgroup generated by small a2, and it turned out that these two cyclic subgroups intersect trivially. That is, there is only the identity element common to both of them, and as a result the order of their product is equal to the product of their orders, and we get this. We did this much, but then let's see what the next step is. You remember, after considering this, we then had to consider, had to means we did consider this quotient group. In this step also, in this next step, we are again going to consider a quotient group. This time, the quotient group of G by the product A1, A2. And there we are going to consider an element having maximum possible order. This also we did in this case. We actually first considered this group and then chose an element in this group having maximal possible order. Okay, so in this step, this is how things go. Let A1, A2, B3 belonging to G quotient A1, A2 be of maximal order. Now this order, just like the other orders, will be a power of p, say p to the power n3. Alright. Now if n3 turns out to be 0, then the process stops, the proof actually stops, because we then have this. Because if this is the maximal order, you see, just think about it. If n3 is, it has to be 0, that means the maximal order in this group of any element is 1. And that happens only when there is nothing other than the identity element in the group, because its order is 1. Any other element, every non-identity element, if it has finite order, then it cannot be 1. It will be greater than 1. That is why, if this is the case, then this quotient group is identity. But in that case, G has to be equal to A1, A2. But then our proof just stops. We have shown that G is the direct product of these two cyclic groups, A1 and A2. And we are done. Let's just add that also. So, let n3 be positive. Okay. Now, since Now let's recall from the previous step that this is an element of G slash A1 of maximal order, I think it was p to the power n2, yes. Because of this, we have okay, so let us now see what happens if we consider this element. We have to be rather careful with these numbers. Here we have A1 and B3, which is this B3, but the exponent is p to the power n2. Okay, so this becomes A1B3 to the power p to the power n2. It must be equal to A1. Why is this so? You see, we have already discussed about this. We discussed it in the previous video itself. If you have maximum possible order and take that as exponent and form a power of any element of your group, that is going to give you the identity element. Now the element whose order was this p to the power n2 is A1B2, and that of course is coming from this quotient group, and this A1B3 is another element. Okay, so its power corresponding to this exponent is also going to be A1 due to the maximality of p to the power n2. Exactly how we did the calculation in the previous video itself. So that's how we have this. This implies that B3 to the power p to the power n2 belongs to A1, and hence B3 to the power p to the power n2 also automatically belongs to A1A2. Why? Because A1 is itself contained in A1A2. Hence, N3 has to be less than or equal to N2. Oh, but before that, of course, we have something else that we did in the previous step, and a similar thing is true here also. So we just simply write like this: like the above paragraph, or let me just also write just like the above paragraph. Above paragraph means the paragraph that we saw in the previous video. Okay, so there, after a similar step, you see, we are not just going on doing things arbitrarily. The pattern of the argument here is just like what we saw there in the previous step. So this time around, p to the power n3 is the largest positive integer such that b3 to the power p to the power n3 belongs to a1 a2. Yeah. I haven't made any mistake here, okay. Here this statement is about b3 to the power p to the power n2. However, this one is about p to the power n3. If you go to the previous step, you will see the similarity. And this is why, hence, N3 is at most N2. Alright. Now, yeah, of course, so this is an element in which the exponent is the highest possible, such that this power of B3 belongs to A1, A2. Now, being an element of A1, A2, it has a specific form. So, let us consider that now. Because we know that A1 is a cyclic group generated by small a1 and A2 is a cyclic group generated by small a2. And that is why B3 to the power P to the power N3 is going to be of this form: A1 to the power I1 times A2 to the power I2 for some integers I1 and I2. Again, I am repeating that by capital J we denote the set of integers in this book. Alright, now what consequence will this have? Note that, yeah, this next thing is, okay, let's see where these calculations take us. Note that it seems just out of the blue we are bringing in terms, but of course every step has a purpose. Note that A1 to the power I1 times P to the power N2 minus N3 times A2 to the power I2 times, again that same thing, P to the power N2 minus N3. Many mosquitoes entered today. Yeah, I am having problem. Now, since we are in an abelian group, so we can of course write this N2 minus N3. Okay. If we don't write these things carefully and nicely, then we will get really very confused about suffix, exponents, superfix, this type of things. And what is this? This is just B3 to the power P to the power N3 N2 minus N3. Now we can use one of the rules of exponents. And using that rule, and then of course you know what will happen, we will end up having this B3 to the power P to the power N2, and this of course belongs to A1. Okay. Now what? Now note that, oh, where is this coming from? You just go before this line, it's there. Now note one thing, that what is it that we have shown here? This element times this element belongs to A1. However, only this power of small a1 is already in capital A1. Why? Because capital A1 is the cyclic subgroup generated by this, which means that this other element also must be in A1, because after all A1 is a subgroup. And so A2 to the power I2 times P to the power N2 minus N3, yeah, minus is there. This has to belong to A1. But we also have, okay, now let us also consider the fact that this is, after all, this element is a power of A2, and capital A2 is the cyclic subgroup generated by that small a2. So this power of A2 will simultaneously belong to capital A2 as well. P to the power N2 minus N3 belongs to A2. So it belongs to both A1 and A2. That means it belongs to their intersection, which however is trivial, since we have this. So A2 to the power I2 times P to the power N2 minus N3 is equal to E. Alright. So from this last equation, we conclude that the order of A2, by a previous property, we have been using it many times. Okay. The order of the base A2 has to divide the exponent. What is the order of the base? P to the power N2. This implies P to the power N2 divides I2 times P to the power N2 minus N3, and that which in turn implies what? P to the power N3 divides I2. Okay, how exactly, that we have already seen one such example in the previous step, in the previous video. So I'm not going to elaborate on that. Okay, so we do get this. Okay, so after this, what is it that we have to do? Also, another such calculation is there. Yeah, that's what probably makes this proof slightly complicated. It's not immediately apparent. Even if you are told what to do, you get easily confused and are lost in the jungle of these steps. Also, it took me quite a while to really streamline these things, okay, like this. Also, so the next calculation is what? Okay, this time we are considering this power of A1. A1 to the power I1 times P to the power N1 minus N3, not N2. Okay, we will see where this leads us. And this becomes A1 to the power I1 times P to the power N1 minus N3 times, now we are going to introduce another term, a similar power of A2 to the power I2 times this times, let me write it here, A2 to the power minus I2 times P to the power N1 minus N3, so that these two cancel out and we are left with this. However, again, now you know where this calculation is taking us, because we are in an abelian group. N1 minus N3 times, we have to keep writing this. And what is this? Is it b3? Oh, it's not simply b3 but b3 to the power p to the power n3. Did we use this exact thing in the previous calculation? How are we getting p? Oh, after, okay. After adjusting the exponent which lies there outside. Okay, fine. There is no mistake. A2 to the power minus I2 times p to the power n1 minus n3. b3 to the power, so this becomes p to the power n1 times this. This I believe is going to be E. Why? That's because b3 after all is an element of capital G, and if you remember, p to the power n1 is the largest maximal power of elements of G, and that is why this will become identity. Is that what I did? Yes. So let's just write one more line just to emphasize the fact that this becomes identity. That means we will be having this power of A2. Okay. I think the hard part is over. All right. Oh, so, okay. Now you see the interesting thing. We started with a power of A1 and we proved that that is also a power of A2, which means that this element is a power of A1 as well as the power of A2, and that is why it belongs to the intersection of these two cyclic groups, and that is trivial. We are milking this as much as possible, this thing that is available to us. Alright, so from this what are we going to get then? Oh, so this just simply of course this and this will both be equal to identity, but right now we need the fact that this is identity. So which implies, again same argument, the order of A1 this time will divide this exponent, and the order of A1 is p to the power n1, the largest possible order. Which in turn implies that p to the power n3 divides I1. Alright, I forgot the previous divisibility relation. Here we have got p to the power n3 dividing I1, and a while ago, so we also saw that p to the power n3 divides I2 as well, okay, and it's also dividing I1. So that means both I1 and I2 are multiples of p to the power n3. That is why let I1 be this multiple, say j1 times p to the power n3, and I2 be j2 times p to the power n3. For some, no, this doesn't sound right, where J1 and J2 are integers. Okay. So, after having these expressions, what type of form now b3 to the power p to the power n3 takes? b3 to the power p to the power n3 now becomes what? Of course, we remember that this is a1 to the power I1 times a2 to the power I2. So, a1 to the power j1 times p to the power n3 times a2 to the power j2 times p to the power n3. And keep in mind that we are in an abelian group. And now is the time finally for us to choose A3. You remember, after doing some calculations in the previous step, only we were able to choose the element A2. But now we are able to choose A3, which will give us another cyclic group. And that A3 is going to be, we can, however, add one more step here. A1 to the power j1 times a2 to the power j2 whole to the power p to the power n3, again because of the fact that we are in an abelian group. Now, let a3 be, I do not want to mess this up by writing the wrong thing. First, we have to take a1 to the power minus j1, then a2 to the power minus j2, and then b3. If you take this entire thing on that side, use the rules of exponents and the fact that you are in an abelian group, you get the fact that a3 to the power p to the power n3 is equal to identity. And simultaneously, we are also denoting by capital A3 the cyclic subgroup generated by small a3. And then only we mention that the power of a3, where the exponent is p to the power n3, is e. Note that this is equal to e. But that is just one thing, okay. This by itself won't tell you that the order of a3 is p to the power n3. It has to be the smallest such number. Okay, that also we have to show. So let's suppose that it's not, and then arrive at a contradiction. Suppose a3 to the power s is equal to e for some integer s, positive integer, less than p to the power n3. What will go wrong then? Then again a sequence of steps. Let us see the s power of b3. Okay, so this, what can we write in its place? We are going to have to introduce terms by adjusting things. a1 to the power minus j1s times a2 to the power minus j2s times a1 to the power j1s a2 to the power j2s b3. Or did I write, hold on, did I write the, exact opposite thing I wrote. This is not what I want here, I want the minus s here, b3 to the power s. And note that you do not have to care for the order in which you write. I mean, of course, with A2 you are getting A1, but you can switch the order because we are in an abelian group. Otherwise, this will give you a wrong result. In a generally non-abelian group, you cannot do this. But anyway, again, because of the fact that we are in an abelian group, I think here I forgot to see. Again, using the fact that we are in an abelian group, you get this minus J1 minus J2 B3 to the power S. And this thing is nothing but A3. Okay, and we have supposed that A3 to the power S is identity. So this becomes A1 to the power J1S times A2 to the power J2S. But what is the problem then? Oh, okay. So because of the form of this element, it belongs to A1, A2. And that is a problem. Why? Because it contradicts the minimality of p to the power n3. But wait, just hold on. I think I wrote something wrongly. If it contradicts the minimality of p to the power n3, I am a little confused here. What is n3? Oh, okay, yeah. Okay, now I understood. But I will explain. Let me first write. But this contradicts the minimality of p to the power n3. What minimality? Let's explain it here. You see, well, the calculation does not directly contradict anything, but the calculation immediately gives us something which is contradictory. What have we shown here? We have shown here ultimately that this power of B3 belongs to A1, A2. What does that mean? It means that A1, A2, B3 to the power S equal to A1, A2, B3 to the power S, that is equal to A1, A2. Why? Because B3 to the power S belongs to this subgroup A1, A2. Do not confuse yourself by thinking, oh, we have two subgroups. No, this product itself is a subgroup. It may not be a cyclic subgroup itself, but it's a subgroup, okay? And this is a coset of that subgroup. So if the representative element belongs to the subgroup itself, then the coset is just the subgroup, okay? However, what is p to the power n3? P to the power n3 is nothing but the order of this element. In this quotient group, which means that no positive integral power of this coset where the exponent is smaller than p to the power n3 should give you the identity element A1, A2 of this group. But that is exactly what we see in this calculation. S is a positive exponent less than p to the power n3, such that the corresponding power of this element is the identity element in the relevant group. That is the contradiction. And that is the minimality of p to the power n3 as the order of this element which is being violated due to our erroneous supposition. That means our supposition must be wrong. So, our supposition is wrong. But then that along with this proves that the order of A3 has to be equal to p to the power n3. Hence, order of A3 is equal to p to the power n3. But we are not done yet, not even in this step. There is one more thing we need to do. We need to prove now that this new cyclic group, capital A3, intersects the product A1, A2 trivially. That also is there. And for that, we are next going to consider now, so we are going to consider a common element. An arbitrary element of capital A3 looks like this. Some power of its generator, small a3. Suppose some such power belongs to A1, A2. For some integer t. Okay, then what happens then? Then A1 to the power minus J1, A2 to the power minus J2. Oh, okay, let us also take t with these things. Times A3 to the power t belongs to A1, A2. How? You see, the form of this element, this power of A1 times this power of A2, of course, this will be an element in A1, A2. And this, according to our assumption, is also an element in A1, A2. Since A1, A2 is a subgroup, so their product is again in A1, A2. That is, however, our choice is not arbitrary. We have carefully chosen this. A2 to the power minus J2 times A3 to the power t, or okay. If I am taking A3, okay, with A3 I won't get anything if I take minus, but I would have to take plus. So let me just make this B3, okay, but then I cannot argue like this. Then no, I cannot immediately say that this belongs to something. I have to see what the element is. Let me just keep the line like this, and now I am considering this element. This becomes A1 to the power minus J1 times A2 to the power minus J2 times B3 whole to the power t, due to the fact that we are in an abelian group. I wrote A3 here, which is wrong, okay, but that won't get us anywhere. Alright, now this is A3, this element. That means you have A3 to the power t, which of course by our assumption belongs to A1, A2. Alright. However, this element already belongs to A1, A2. I was thinking about that before doing this calculation, so that created the confusion. Yeah, now we can use the fact that this element, just forget about this power of B3. This element, due to its form, belongs to A1, A2. Since, let's just write that also, minus J1T times A2 to the power minus J2T belongs to A1, A2, we thus have B3 to the power T in A1, A2. However, we already know something about the powers of B3 which belong to A1, A2. Namely, the minimal such power is P to the power N3. So, the minimality of P to the power N3 then implies that not only is P to the power N3 less than or equal to T, but actually it divides T. How, that also we have seen before. Okay. It divides T. But at the same time, also P to the power N3 is actually the order of A3. Hence, A3 to the power T. So, T will appear as what? A multiple of P to the power N3, which is the order of A3. So, one application of one of the rules of exponents will make this identity. So, that's it. So, you chose this arbitrary element from capital A3 also in A1, A2, and it turned out to be identity. Thus, A3 intersection A1, A2. So that we do not have any confusion about what we are doing, I have used parenthesis. This is equal to E, and we have order of A1, A2, A3 equal to this time. This is the final result of the step that we went through today. This is going to be P to the power N1 plus N2 plus N3. Now that you have two steps, you can compare them. Okay, what we did in the previous step and what we did today. What pattern emerges? That you have to see. And that pattern actually, you should see that, understand that, and convince yourself that okay, it can be continued and until we exhaust the group G. Because you see, every time we are getting a new cyclic group, the order is increasing. Because G is finite, this process will eventually exhaust all of the elements of G. And by the time it does that, we will have expressed G as a product of cyclic groups. However, that time hasn't come yet. That's because these are only two steps. Okay, I am going to stop it here itself today. So I want you to go through these two steps, gain the proper understanding, and then just to test that we have really understood the steps, and we have really understood means we can really see the second step as a continuation of the first step, having the same pattern. So to test that, we will do one more step in the next video, and with that step the proof will be over. I mean, after that, after completing that step, which of course will involve another cyclic subgroup. Okay, and the next step will start by mentioning that this is also not the order of G. that there is still room for more elements. And then we will go through a similar process. But because we already have gone through 2 steps, so we can afford to be a little sketchy in the next step. And then we will mention, of course, that since G is finite, this process will eventually terminate, and that will give us our results. So that's just it for tonight. See you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.